Welcome, honors students. Today we're going to begin our chapter 14.2 and actually begin to work with what's called the gas laws. Now there's several gas laws. We're going to introduce this slowly, begin to work problems within it so that everybody has the opportunity to learn how to work with the formulas that are involved in the gas laws. But in 14.1, we talked about the properties of gas. Well, we learned it in the last chapter that a gas moves is constant, its movement's constant, rapid, and random. And with that being said, we also learned a term in the last virtual lesson, compressibility, that there's a lot of space between these gas molecules so they can be actually compressed and pushed closer together or expanded apart because there's no attraction, so they'll fill whatever container size they're placed in. We also learned that there are some factors that come into play when you're dealing with a gas. Temperature. If you are applying more energy, some kinetic energy to those gas molecules, they're going to move faster. As a result of them moving faster, they're going to strike whatever they might be in, whatever container, with more force. So there's a relationship to temperature. There's a relationship to the volume of the container. If you have a big container and you make it smaller, now the pressure is going to go up. So there's a relationship of temperature. There's a relationship of volume, how much gas you have in a container. So that would be moles. And then there's pressure. So all four of those factors, temperature, volume, moles, and pressure, all have relationship. And that's what this section begins to cover, the relationship of gas. Please do make sure that you take the opportunity to watch these virtual lessons. I know in looking back on the YouTube videos that I have posted, there's a few that only have around 20 views, and I have almost 70 students, 67 students. So that's not a good percent watching. And if you want to do well, it's imperative that you watch these videos, you take good notes, look at the example problems that I do, write them down, maybe pause the video to try and work the problem first, and then you'll be able to learn the process. All right, so with that being said, welcome. So when we talk about how do you fill up a hot air balloon, so a hot air balloon works on the principles that warm air is less dense than cold air, so hot air rises. If you heat the gas, it's going to expand because it has more energy, so it's going to be moving faster, and it's going to be able to lift that balloon, and that is the principle that these hot air balloons work on. We're going to talk about them a little bit later on. So Boyle's Law. So please, in your notes, Boyle's Law, that's really important. We're going to talk about a graph. You need to know graphs. So we're going to talk about graphs of Boyle's Law, Charles' Law, Gay-Lussac's Law. So there's quite a few laws we're going to talk about. How are the pressure and volumes of a gas related? That's our key concept from Boyle's Law. So key, if the pressure is constant, sorry, the temperature, if the temperature is constant, as the pressure of a gas increases, the volume decreases. So think about this for a second. If you have a container, you take some kind of a plunger mechanism and you have it here, and then in the next part of the container you push it down, so the volume decrease, the pressure increase. So as the volume decrease, the pressure increase. So as the pressure decreases, the volume increases. So if you take the volume and you expand it, now your pressure is going to be less. So that's a relationship. It's an inverse relationship. Very important that you write that down, an inverse relationship. So pressure to volume is inverse. So Boyle's Law, you can define it now, please. And this is a formula. So Boyle's Law states that for a given mass of gas at constant temperature, so you have a constant amount of moles and the temperature is constant. So those two are held constant, so they're not changing. The volume of the gas varies inversely with pressure. And here is our formula. Pressure 1 times volume 1 equals pressure 2 times volume 2. So Boyle's Law states that for a given mass of gas at constant temperature, the volume of gas varies inversely with pressure. All right, so we have a few things there. So moles, we learn moles is represented as N. So N is going to be constant, and so is temperature. They're held constant. So you don't have to worry about them. And we'll look at that a little bit more later. All right, so here's this graph. This graph is really important. So let's look at this graph. On the test for this particular chapter, you will have to recognize graphs for each of the three main gas laws, Boyle's, Charles, and Gay-Lussac's law. So this is important that you get down. So when you read this, if you're looking here, so say you start off with a volume of 2.5 liters. And you take that volume and you decrease that volume. Look at what's happening to your pressure, and your pressure is over here on the y-axis. So as you decrease the volume, the pressure increases. So this is a curved line. It's a curved line. It's not straight. You're going to see the other graphs are going to be straight lines, but this one's a curved line. That is an inverse relationship. So as you go down further, you get down here to 0.5, look at what happens to your pressure. Extremely high versus if you were at 2.5 liters. Same thing goes into effect. If you expand your volume, your pressure will fall. So that is your inverse, and your curved line is representing Boyle's Law. So let's look at an example problem. How can you solve a Boyle's Law problem? So a balloon contains 30 liters of helium gas at 103 kilopascals. What is the volume of the helium when the balloon rises to an altitude where the pressure is only 25? So you went from 103 kilopascals, you fell down to 25 kilopascals. Assume you're in a balloon, so you're not adding any more volume of gas, you're not adding moles. So that's held constant, and assuming that the temperature is going to be the same. So what do? You always write down everything that's given to you. And that's what it's showing you to do. And I'm going to do some examples today, and I'm going to show you the same thing. Write down everything you are given. So you know pressure 1, you know volume 1, you know pressure 2. You do not know your volume 2. So with that being said, you get your formula, which is right here, P1V1 equals P2V2. And then you can manipulate that formula. So when I say manipulate that formula, is just isolate the variable that you're solving for. So to isolate V2, all you got to do is divide by P2, and that is what you see right here. They divided by P2, and that gives you what you have to use, the formula in the proper format. So now all you got to do is plug in. So what exactly they do? They plug in their pressures, they plug in their volume, they solve, plug in their calculator, and here you have your volume 2 rounded to the correct significant figures is 1.24 times 10 to the 2 liters. So it has expanded from 30 liters to 124 liters. So then you evaluate, does it make sense? Yes, actually, it does make sense if you look at it. So let's look at an example here. A sample of neon gas occupies a volume of 677 milliliters at 134 kilopascals. What is the pressure of the sample if the volume is decreased to 642? So you are pulling the volume down, you're decreasing it. So you should think, I'm decreasing my volume, my pressure should go up. So now let's write down everything that we know. So we have our P1, our V1, our P2, our V2. And let's come here and write this down. So our pressure 1 is 134 kilopascals. Our volume 1 is 677 milliliters. Our pressure 2 is what we're solving for, blank kilopascals. And our volume 2 is equal to 642 milliliters. So now I'm going to write down my formula. So I have P1V1 equals P2V2. And I'm solving for pressure 2. So I'm going to divide both sides by V2. And that cancels off. So now I have, and I'm just going to put this exactly how it's written here, P1 V1 over V2 equals my pressure secondary. So I'm going to plug in exactly what you see happen here. So pressure 1 is 134 kilopascals, parentheses. My volume 1 is 677 milliliters. And I'm going to divide that by my volume 2, which is 642 milliliters. And I'm going to put these all in parentheses. If you look what happens, my milliliters cancel off. So now I'm just going to get my calculator, and I'm going to plug this in. So I'm going to go 134 times 677, and I'm going to divide that by 642. So I have to be rounded to, let's see here, 3 significant figures. So if I plug this in, I get 141 kilopascals, and that is my pressure 2. So I can come over here and I can write that in, 141 kilopascals. So when I look at this, I decreased my volume, so my pressure went up, and that's exactly what happened. I went from 134 kilopascals to 141 kilopascals. And once again, they're just going to walk you through the exact same thing that I did. Now I have a couple other problems. I want to take a moment and look at these problems and maybe give them a try. Pause the video, work on it, come back and see how I solve them. So we have here dinitrogen monoxide is held in a 2.5 liter flexible container at 105.0 kilopascals. If the temperature is held constant, what will be the new volume if the pressure drops to 40.5 kilopascals? So once again, I write down everything that's given. When I look at this, it tells me the temperature is constant. So that's what alerts me that this is actually Boyle's Law. I don't have to worry about temperature. So I'll write down, I have P1 V1 equals P2 V2. So now I'm going to write down all my information. My pressure 1, it says, is 105.0 kilopascals. My volume 1 is 2.50 liters. My pressure 2 is going to be 40.5 kilopascals. And my volume 2 is equal to blank liters. So that's what I'm solving for. So now I can just rearrange my formula right here. I am going to solve for volume 2. So I'm going to divide both sides by P2. And that'll get rid of it here. So now we're writing this, P1 V1 divided by P2 equals my volume final, my final volume. So plugging right in here, I have 105.0 kilopascals. My volume 1 is 2.50 liters, and I'm going to divide that by my pressure 2, which is 40.5 kilopascals. kilopascals, and I put that in parentheses. Notice right away my kPAs cancel, and that leaves me liters, and that's the unit I needed to be in. So now I'll plug this in my calculator. 105.0 times 2.50. I'm going to divide that by 40.5. So I need to be at 3 significant figures. So I have 6.48. 6.48 liters. That is going to be my new volume. So I can come over here and write this down. 6.48 liters. All right? That is solving this particular problem. So now let's look at one more. A gas with a volume of 4 liters at a pressure of 205 kilopascals is allowed to expand to a volume of 12 liters. What will be the new pressure in the container if the temperature is held constant? So read that over, maybe pause the video, grab your notes, and maybe try to work this problem out in your notes. All right, so once again, let's look at what it says here. Temperature is held constant, so I'm not going to deal with temperature, so that alerts me right away that I am dealing with my Boyle's Law. So that is my P1 V1 equals P2 V2. So I'm going to start writing down all my information. So my first pressure is 205.0 kilopascals. My volume initial is 4.00 liters. My pressure secondary is what I'm solving for, and that's going to be kilopascals. And then my secondary volume, it says it went up to 12.0 liters. So I'm solving for pressure, my secondary pressure. So to get rid of that, I'm going to divide by V2 and cancel it from the one side, and now I can rewrite this. So now I have P1 V1 divided by V2 equals my final pressure. So now I can plug in to this formula. So I'm going to go 205.0, and this is kilopascals, parentheses. My volume 1, my initial volume is 4.00 liters. And I'm going to divide that by my volume 2, which is 12.0 liters in parentheses. And I'm going to cancel off my liters, and that's going to leave me the units that I need, which is kilopascals. So I get my calculator again. So I go 205 times 4.00 divided by 12. All right. So with that being said, I need to be at 3 significant figures. So looking at my calculator, it should be 68.3, and this is kilopascals. So I can come back over here and write this down. So 68.3 kilopascals. So my volume expanded basically 3 times. Look at what my pressure did. It fell down to from 205 kilopascals to 68.3 kilopascals. Okay, so our next virtual lesson is going to be over Charles's Law. So I'm going to stop here today. We've done 3 problems together. There's an example problem in the PowerPoint for you. They're all on Moodle. I loaded them all up already. Please take the time to look this over. Take some good notes in this section. Try working these problems. Now, we're going to work a lot of problems in this section, so please be prepared for that. But it's important to have the ability to read and interpret what type of problem. This is here Boyle's Law. How do I know it's Boyle's Law? Because it's telling me I'm dealing with pressure and volume, and temperature is held constant. Thanks for watching. Have a good day.